Recall that quantitative variables are those characteristics that we can measure with numbers, and they can come in discrete and continuous varieties. That is, in the case of discrete variables measured as integer counts, or in the case of continuous variables measured on a continuous number line. We have a few more options for depicting quantitative variables relative to the bar graph and pie chart options for qualitative variables. We'll discuss a few basic ideas, providing a foundation for exploring other more sophisticated techniques after this course. A little notation first. Let's refer to a variable with a capital letter and the observations of that variable with lowercase letters. That is, if we're measuring the dimensions of a bolt produced by a machine shop, variable capital Y might be the diameter of the bolt in millimeters, and the measurement of the diameter of the ith bolt is represented as Y sub I. If the third bolt in our sample has a diameter of 2.65 millimeters, then Y3 equals 2.65 millimeters. Generally, N refers to the size of the sample. If we collect a sample of 35 bolts, then N equals 35. The most popular means to depict quantitative data is with a histogram. Similar in concept to a bar graph, the horizontal axis of a histogram is a quantitative variable that is divided into classes or ranges of values, with the vertical axis displaying the counts of observations in each of those classes. There are several ways to determine how many classes should be chosen, but the rule of thumb I typically choose is to take the square root of the sample size n and round up to the nearest integer. Rounding up to the smallest following integer is usually represented with the ceiling function, whereas the floor function would indicate that the value should be rounded down to the nearest integer. The width of each class is found by taking the range of the entire sample of observations, the maximum value minus the minimum value, and dividing by the number of classes. If the data you've collected are integers, I suggest rounding up to the next integer on the class width calculation as well, to make sure all values are included in the histogram. The histogram is then constructed as follows. Take the minimum observation from the sample, or perhaps round down to the nearest integer, such that the bounds of the histogram are integer values. Add to it the class width to generate the first class, then continue generating classes by adding the class widths until the number of classes is reached. Then count the number of observations that lie within each class and create a bar that corresponds to the appropriate frequency on the vertical axis. The appearance of the histogram differs from the bar graph in that the bars on the histogram should be touching, suggesting the continuous nature of the horizontal axis. Say you're an industrial engineer hired by Babu Bhatt to study the food preparation process at his failing Pakistani restaurant, the Dream Cafe. You collect a random and representative sample of n equals 75 customers to the cafe, and you measure the length of time, in minutes, that each customer waits for his or her order. Let's take a look at the data and generate a histogram. We first find the number of classes as the square root of 75, which is 8.66. We round up to 9, so we'll divide our data into 9 different classes along the horizontal axis. The width of those classes is found by taking the range of the data and dividing by 9. The maximum observation of customer wait time is 20.3 minutes, and the minimum observation is 4.1 minutes. The range is 20.3 minus 4.1, or 16.2 minutes wide. The class width is 16.2 divided by 9, or 1.8. We start with 4.1 and keep adding 1.8 to generate 9 classes. How do we determine where the bounds of each class lie? This is arbitrary, but should be consistent. I suggest including the lower bound of the class in that class. In this case, the smallest class of the histogram will range from 4.1 to 5.9. 4.1 is included in the first class, 5.9 will be the lower bound on the next class, and therefore will be included in the next class up. Another way to say that is the first, leftmost class is greater than or equal to 4.1, and strictly less than and not including 5.9. The second class would be greater than or equal to 5.9 and strictly less than 7.7, and so on. Naturally, all the observations we collected have to be accounted for, so we'll have to make an exception for the largest value in this case, and make sure it's in the rightmost class. Note that we could label the vertical axis with either frequency or with relative frequency. What do histograms tell us? Generally speaking, they tell us how data are distributed. Is there one particular class that stands out as being more frequent? Is the distribution symmetric? Is the distribution of data skewed in one direction or another? Here are some examples of what we might learn from particular histograms. The first histogram is symmetric about the mean and diminishes toward both tails. This suggests that a bell-shaped pattern may describe the data, and this has implications for our discussion of probability distributions later in the course. The center of the data also appears to be most likely, as the class in the middle has the highest frequency. We could also see a bimodal pattern, where the distribution is still generally symmetric about the mean, but it has two different most likely values. This might suggest that the data that we've collected may come from two different distributions. For example, consider a contrived data set where we collected several observations of women and men and measure their heights. All mixed together, we might detect a bimodal distribution for height. This might lead us to investigate why the distribution looks the way it does. One reason might be that the sample is made up of members from populations that have different distributions of height. In this case, women and men. Splitting the samples according to the two populations might show us two different representations. A histogram may indicate skewness, or where particularly large or small values in the data skew the histogram in one direction or another. Right skewness is seen when there is an elongated upper tail, and a histogram that is skewed to the left has an elongated lower tail or particularly small values. One last basic pattern we may see in a histogram is uniformity, or where each class along the horizontal axis is roughly equally likely to occur, or their frequencies are roughly the same. This kind of pattern suggests that no observation is more likely to occur than another. Rather than plotting frequency or relative frequency on the vertical axis, we could plot the cumulative frequency, which essentially keeps a running sum of frequencies as we increase the classes along the horizontal axis. Such a plot tells us how many observations fall below a particular value on the horizontal axis. Let's briefly chat about a few other graphical depiction techniques for depicting quantitative data. An Ogilvy chart is similar to a cumulative frequency histogram, representing the upper bounds on the class widths with dots connected with lines. It's a little less cluttered than a histogram, so the presentation of the cumulative trend is cleaner. For a small sample data set, and particularly for a set of integers, a stem and leaf diagram is useful for displaying a trend while also showing the actual values collected. For example, see our data set of integer exam scores for a sample of n equals 30 students. In this case, the tens spot stays constant, and the ones spot changes in the stem and leaf diagram in order of the data collection. Viewed on its side, it looks something like a histogram, providing a depiction of the frequency of each 10 value. Plus, we get to see the actual values that make up the shape, in case that matters to us. Say we've collected values of two variables for each observation in a sample. Perhaps the frequency of observations as each variable changes might tell a story. A CrossTabulation chart allows us to see the frequencies of observations that fall at the intersection of two variables. These are especially good for qualitative variables, but we can discretize quantitative variables as well. Let's say we're doing an ergonomics study at a large factory, and we're interested in how operators feel about the lighting conditions on the factory floor. We have a sample of 177 operators, and we collected two variables. The first is a Likert ordinal scale response to the question, are you satisfied with the lighting conditions you experience on the factory floor? Measured on a scale from 1, representing not at all satisfied, to 5, representing very satisfied. The second variable was the age of the operator, a quantitative variable, which we discretized into three categories: under 30, 30 to 50, and over 50. The number of categories should be chosen such that they're meaningful from an analysis standpoint. We get an idea of the count of operators in each category, noting that there are fewer operators in the sample that are over 50 relative to the other age groups. We see that most operators fall in the middle of the satisfaction survey, with not at all satisfied having the fewest responses. Further, we see that the operators under 30 tend to be less satisfied with the lighting situation, and operators over 50 tend to be more satisfied. Seeing how these two variables vary with each other might add some insight for further investigation. For example, why exactly might different age groups have different opinions on the lighting used in the factory? Another tool for depicting the relationship between two quantitative variables, where we believe one variable influences the other, is a scatter plot. With a scatter plot, the independent variable, or the variable that we think is causing the influence, spans the horizontal axis, and the dependent variable, or the variable that we believe is being influenced, runs along the vertical axis. A point on the scatter plot represents an observation in the sample that has a value for each variable. For example, let's take a look at some data from Kruger Industrial Smoothing, which polishes ball bearings for use in aircraft. Polishing machine operators are paid partially according to a piece rate system, wherein if they work faster and produce more parts, they are eligible for monthly bonuses. Kruger management suspects that this method of pay may contribute to a high number of defective parts. As a quality control manager, you check the average times to polish a type of bearing for 10 different employees during 20 days selected at random during the last month, determining the corresponding percentage of defective parts. The scatter plot shows the relationship between percentage of defective parts, the dependent variable on the vertical axis, and the average polishing times, the independent variable along the horizontal axis. With a scatter plot, we might see a positive relationship. That is, as the independent variable increases, we may see an increasing dependent variable, or we may see a negative relationship. An increasing independent variable leads to a decreasing dependent variable, or perhaps no relationship at all. With our polishing time data, we see that as polishing time increases, we see a decrease in the percentage of defective ball bearings. That is, there's a negative or inverse relationship between defects and polishing time. And such a conclusion makes intuitive sense. The more time spent on getting the operation right, the fewer problems will result. Depicting data through charts and graphs can help a lot, and your boss will probably like to see them. But graphical depictions on their own don't mean a great deal. You should always think, what information can I extract from this? Think about that when you're doing your homework assignments and exams for this course. The answer to a homework problem is not a histogram. It's not even the histogram exhibits right skewness. The answer is in the implication of right skewness to the particular problem context you're studying. The graphical techniques allow us to make some general observations about the shape and spread of the data. A more complete understanding can be gained with descriptive statistics. Descriptive statistics are numerical measures that quantify the central tendency of the data and the dispersion of the data. Measures of central tendency generally quantify the center of a data set. Three common measures of central tendency are mean, median, and mode. The mean of a data set is simply its numerical average. Arithmetically, that's the sum of the observations divided by the number of observations. In this lecture, we focused on results of a sample, as that's typically how we'll collect and observe data. However, we should distinguish between the notation for a population and a sample from that population. If we know the entire population of size capital N, and we want to describe the mean performance of the population, that's the sum of the capital N observations divided by capital N. We refer to the mean of a population with mu. If we define our population as something very specific, say the employees that work the day shift at a small factory, then we can likely collect the values of a variable from the entire population. But often, the population is something large and unmanageable. For example, if we're measuring the driving behavior of all drivers in Oklahoma, it would be difficult to measure all capital N drivers, or even know exactly the size of capital N in the first place. As such, we must also have a measure for the mean of a sample, which looks similar to the calculation of the population mean. The sum of y sub I values for I equals 1 to sample size little n divided by little n. We refer to the sample mean as y bar. We can use the mean as a measure of central tendency for ratio data. The median is the middle value of a data set that has been ranked in increasing or decreasing order. If the number of observations is odd, the median is the middle term. If the number of observations is even, the median is the average of the two middle terms. Some textbooks use m to refer to the median, others use y tilde, as opposed to y bar that represents the sample mean. We can use the median when describing the central tendency of ordinal or ratio data. The popularity of the median for ratio data is that its value is not influenced by outliers, or observations that are uncharacteristically large or small. Let's look at a small sample of size n equals 11 observations of a variable. We see that the 7th observation is particularly large relative to the others. The mean accounts for raw values of data, not just their place in the data set from lowest to highest. The median of these 11 observations, on the other hand, is 3.2, something much more in line with most of the values in the data set. The median is not influenced by the value of the 7th observation. To see the influence that this large value has on the mean, let's say Y7 was 4.3 instead of 12.4. The median would still be 3.2, but the mean would be 3.14 rather than 3.94. It's nice to include the median as a measure of central tendency, along with the mean, to account for any outliers. The mode is the value that occurs with the highest frequency in a data set. In other words, it's the most likely value to occur. In our previous sample of 11 observations, we see that the value 3.2 occurs twice, where all other values occur just once. As such, the mode of the data set would be 3.2. Going back to our food preparation time example at the Dream Cafe, we can use a histogram to find that the mode of the classes in that data set is the class ranging from 7.7 to 9.5 minutes. The mode may not necessarily exist, as we could have a data set with all unique values, and if the mode does exist, it may not necessarily be unique, as we could have a data set with several values that are observed the same number of times. We can use the mode to measure the central tendency of nominal, that is, each category is most likely to occur, ordinal, or ratio data. Recall 3 of the different histograms we looked at previously, and let's compare the locations of the mean, median, and mode on these histograms. For a symmetric histogram, we see that the mean, median, and mode are all the same. That is, the left and right tails balance each other out, making the mean and the median the same. And the middle value is also the most likely value. In a right-skewed histogram, the mean is skewed to the right by the large observations. The median is the value in the middle, and the most likely value occurs on the left-hand side, as most frequent observations are on the low end of the horizontal axis. The opposite is true for a left-skewed distribution. But we can only learn so much with measures of central tendency. Namely, we only get a sense for where the middle value is. That is, we're taking a data set and shrinking it down to just the middle. That's certainly useful, but it doesn't tell us anything about how dispersed the data are. Here are 3 different data sets that have the same mean, but their dispersions are entirely different. For example, let's look at the throughput of the 7 polishing operators collected for each of 2 shifts at Kruger Industrial Smoothing. The mean throughput per shift is the same, with an average operator throughput of 40 completed ball bearings. But if we plot the throughput of each individual operator, we see a completely different story. In shift 1, all operators perform roughly the same regarding their ball bearing output. That is, the dispersion of operator performance in shift 1 is small or tightly packed. In shift 2, we see something completely different. One operator gets a lot done, one gets very little done, and the operators in between are still pretty dispersed. The variability in shift 2 is greater than that of shift 1. Looking only at a measure of central tendency may not be enough to tell the whole story. Another example that affects us all, waiting in line. The fancy word for a line is a queue, and the mathematical study of lines is called queuing theory. Very exciting stuff. Most service counters, say at a bank or a fast food restaurant, have one of 2 kinds of queue designs. The first is where there is a number, C, of servers behind a counter, and C corresponding lines form for customers to wait for that individual server. When customers enter, they reasonably try to get in the shortest of the C lines. In the second queue design, a single queue is formed, usually with a barrier rope. When the server finishes with a customer, the next customer in front of the single queue approaches the counter. The average waiting time for these 2 designs is roughly the same. However, the variability of waiting time can be much larger in the first design. It happens to all of us, and I think me more than others. You find the shortest line, and you watch as others in a longer line get serviced and move on with their lives. When a customer in the first design takes longer than average, it causes everyone in line behind them to wait longer than they otherwise would have in the second design. The means are about the same, but it's the variability that leads to unhappy customers. The point is, understanding variability is also important. One quick measure of dispersion is the range, or the difference between the largest and smallest values in a data set. The range is common in quality engineering applications when a more complicated measure of dispersion is too costly, or at least were too costly back when most widely used quality control measures were developed. The range works well as an estimate of dispersion, especially for small sample sizes, say n is less than 6 or so. The much more common measure of dispersion is variance. The idea behind variance is to calculate how closely the values in a dataset are clustered around the mean. This is represented by how different each observation is from the mean value, squared, and summed across all observations. For the population variance, when we can actually observe and measure the entire population, we divide by the population size, capital N. Much like the population mean, we refer to the population variance with a Greek letter, sigma squared. For a sample, we calculate sample variance, S squared, by dividing by n minus 1. Why n minus 1 in the denominator of S squared? A simple answer is that sample variance calculations with n in the denominator tend to underestimate the population variance, so a smaller denominator is used. We'll talk about the value n minus 1 later in the course in the context of degrees of freedom. One issue with the variance is that it is measured in squared units of the units of our variable. For example, if we're measuring food preparation time at the Dream Cafe, the variance of preparation time would be in minutes squared. Squared units don't make a whole lot of intuitive sense to us, so we often take the square root of variance. This square root is called the standard deviation. Let's go back to our 11 observations whose mean was 3.94. The variance of this sample would be 8.19 and the standard deviation would be 2.86. Now that we have some measures of central tendency under our belt, let's take a look at one last visualization technique called box plots, or box and whisker plots. These plots depict the median, quartiles, and outliers of a data set. After a set of data is arranged in increasing order, we find the 4 quartiles of the data, or the observations in the data set in between which 25% of the data observations fall. Like the median, the quartiles don't depend on the values of the observations, just how many observations fall in a particular range based on increasing order. Note the values Q1, Q2, and Q3. Q2 is the median. The value of Q1 essentially represents the median of the lower half of the observations, below which the bottom quartile resides. And Q3 represents the median of the upper half of the data. As such, Q1, Q2, and Q3 separate the 4 quartiles. We define the interquartile range as Q3 minus Q1. Using our 11 ordered observations discussed previously, the median is 3.2, with Q1 equal to 2.5 and Q3 equal to 3.8. Another interpretation of these values is, for example, 75% of the observations fall below 3.8. Quartiles on their own don't tell the full story. We want to plot these values on a number line. We want a box formed between Q1 and Q3, and we want to produce fences or whiskers that give an idea of the dispersion of the lower and upper quartiles. To do so, we calculate a lower fence defined as Q1 minus 1.5 times the interquartile range, and an upper fence defined as Q3 plus 1.5 times the interquartile range. From our data set, the lower fence is calculated as 0.55, and the upper fence is 5.75. We draw a box at 2.5 and 3.8, with a line in between at the median 3.2. This box represents the width of the 50% of the observations in the middle of the data set. To the left of this box, we plot the smallest value within the lower fence. The smallest value that resides within 0.55 and 5.75 is 2.3, and we extend the lower whisker to 2.3. To the right of the box, we plot the largest value within the upper fence, which is 4.1. Any values that lie beyond these 2 whiskers are considered outliers, or points that lie beyond 1.5 times the spread of the middle 50% of the data. We have an outlier on the upper side at 12.3, and we represent this outlier with some kind of marker. We'll use a star here. With a box plot, we get an idea about the spread of the middle 50% of the data and where the median lies with respect to that 50%. Here, the median is roughly in the middle of the box. And we get an idea of how wide the dispersion of the entire data set is, including the existence of outliers. This collection of methods, from graphical depictions like histograms and box plots, to numerical measures which describe central tendency and dispersion, help us better relate trends that we observe in a set of quantitative data.